Hi guys, in this video we're going to use basics of test-driven development, and we're going to use the snake game to, basically as an example. Right, so first of all we're going to write a specification for the game. Then we're going to translate that specification into a series of tests, which will represent that specification in code. Then we're going to write the actual game code, which will hopefully pass those tests, and so we can, to a certain extent, prove that the game works. Finally, I'm going to add the view for the game, because for the most part of this video we will be writing the model of the game and also testing that model. And I'm going to use the FXGL framework to write the view. So these are the steps for this video. Right, first step is to write a specification or a brief. So the game runs real time. We know that much. We know that the snake can move in 4 directions. We know that the snake can collide with a food object. We also know that the snake can grow. The snake can also die when it collides with itself. And the snake can also be out of bounds, where bounds refers to the bounds of the game. For the testing framework, I'm going to use JUnit 4. The version 5 is already out if you want to use that. Although certain classes and things will be in different packages. So also the Hamcrest Matcher library is not part of JUnit anymore in the 5th version. So I have to download it as an external library. And for the FXGL, I'm going to use 0.38, but we won't be using FXGL for most of the tutorial. So the basic principle of test-driven development is that you write the test code before you write any production code, where production code refers to the game code in our case. And that's exactly what we're going to do. We're going to write our test first in this package, and I'm going to create a class called snake test. So the first thing we'll need is this annotation called test. Then need to create a method which is going to be testing something. Let's see what is the easiest option that we have here. Well, we could do number 2, because snake can move in 4 directions. That sounds easy. Test snake moves. That's it. So we're going to need snake object, which we don't yet have because we haven't written any code yet. So we're going to kind of predict that there's going to be a class called snake, and we're going to use it as if it already exists. We can move the snake, or we can set direction, because we know that it's going to be real time, so we won't be able to use it to move it by call. We will need to update the state of the snake object in order to move it. And these are somewhat implementation details that I already have in mind, because I kind of know how to implement this since I've already implemented many games that are similar to that. So this is an interesting kind of train of thought, because if you have some basic concepts of the implementation of what you're going to implement, then this could potentially sabotage the test itself. So try not to think about the implementation when you're writing tests. That's the takeaway message. Snake update, and we're going to assert that snake get position, since we're moving, is going to be previous position plus something. So we'll first need to obtain the value of the previous position. Let's call it point TDD. Position, snake, get position. I'm going to add static imports so we don't have too much verbosity. Okay, so position is that. Actually, what we could do is supply the position here, which could be 0, 0, then move to, say, right, then update, which will perform the actual move, and then assert that snake get position is 1, 0. So if we're moving to the right, then we're changing the x value. And this is our first test, which won't compile because nothing exists yet. And based on that, the first thing we need to do is to make this test compile. And this follows the standard rule in test-driven development of red, green, and refactor. So you first have a red test, or try to get a red test. Currently, we don't have any kind of test because that doesn't compile. Then try to write minimal amount of code to pass that test. And finally, refactor both the test and the code to remove various things like duplication or simply hacks or bad code. Sometimes you can even write constants to pass the test, and in the refactor stage you would remove those constants. So we can ask the IDE to pretty much generate stuff for us. So there's the class called snake. Although put it there in the test directory, which I want to do is to create a package in the production directory. So we'll need a constructor that takes point TDD, which is position. We'll need this enum, because direction can be implemented as an enum that has right, left, up, down. So here you can see that I'm not following the standard test-driven development, because I've just written down these things, which are unnecessary to make the test pass. So this is what can be called as hybrid test-driven development, where you kind of mix the tests with obvious implementation. If something can be implemented in a way that you are confident that is true, then you can write the code for that and kind of, do a hand-wavy test kind of thing. So that's what I'm going to use for this video. There are versions, extreme versions of test-driven development, where you write no code at all in production until you have all the tests passing, and you kind of, at all times, you have at least 100% test coverage. Sometimes more if you're writing the test before you write the code. We'll probably need direction as a property, I think. So that would have created the direction as a field, which is fine. We currently don't need a direction. I don't know if we're going to need it at some point, but for now we don't need it, so I'm going to remove that. We also need update, which currently does nothing. And we also need get position. Although that is not string, that's supposed to be point TDD. Right, so we have got some kind of implementation that doesn't really do much. All we need to do now is simply test this, because that should now compile and even run. And it goes red because we don't really do anything. Right, so the first thing, it says that it is expecting this thing, but it got null. So we'll go to get position and see what it returns. Returns the position which is null. We can easily avoid it being null by setting this. We now run the test again, and we know it's not going to be null now. It's something else. It's almost similar, but there is one difference, which is the x value. And how do we get from this to that? Which means those two methods are not working properly, or one of them at least. Right, so we've got direction. That looks about right. Now in the update, all we need to do is set position to position at direction. But direction is an enum, so can't really do much with it. What we could do is go to direction and add the actual direction in the vector format. So right would be 1, 0. Left is -1, 0. Up is 0 and -1. Remember that the positive y-axis goes down in well, actually, we could make it move up because we don't have the view yet. But because I know that the view is going to have this inverted axis kind of thing, it's easier to have one-to-one mapping rather than 1 to -1, in which case we would have to convert the values before we can draw to the screen. And now this becomes direction vector. Cool. Now we have a passing test. So we can, from that, deduce that we can move to one direction, which is right. What we could potentially do is set up other tests and see if we're moving in the right direction in all 4 directions. which means that we could have either 4 tests, or if you're using JUnit 5, then you could have parameterized tests where you pass the parameter to the test. Alternatively, we could write a for loop, which is kind of frowned upon because for loops, well, any kind of loops, add complexity to the test, and you want the test to be as simple as you can make them. Since it's an easy test, I'm going to write a for loop to test all 4 directions so that I can remove that from the list. I'm going to store old position, snake at position. Snake at position should be old position add direction vector. Yeah, so the test passes, which essentially is 4 tests. Now, it is important to understand that this should really translate to parameterized tests because it has a value of 4 tests. So we can remove that now. Another thing that I just noticed is that when you write the test, sometimes you can actually come up with a solution in the test. So by testing that old position add direction vector is pretty much the implementation of what we have here, which is a nice coincidence. Okay, so we've got that. Next thing we're going to do is test something else. Let's add food, because that seems easy. Snake food collision. That's more concise. Again, we're going to create our snake. Let's put it 10, 5. We're going to create food object 10, 5. So they're both placed on the same tile, if you will. Basically, the position is equal. We can now assert. No, I don't want to assert that. I want to assert that it's true. Snake is colliding with food. Again, you do the same process, you complete the same cycle. You start with a red test. You then go to implement the remaining compile errors, completion errors. So, for example, food needs implementation. So I'm going to create class food, which also takes this in the constructor position. Then we implement that method. Food turn false is fine for now. And now we can compile the test, which is what we wanted in the first place. And it fails. So now we need to make it pass, essentially. So how do we know if our snake is colliding with food? Their positions have to be equal. They have to be placed on the same tile. So we can do position equals food get position. and then we implement get position. Still fails because position hasn't been set yet. So we now have another passing test, which is good. So we've implemented this now. The next thing, logically, I think that the test for growth can be implemented. Test snake grows. So essentially, if you think about it, we haven't thought too much about the implementation of any of those things. We're simply following the directions that the tests give us. So essentially what we're trying to do is to make our code pass those tests. New snake grow, and what do we need to assert here? Well, first of all, the length of the snake should increase by 1, and the new element of the snake, or the body part, should be placed in the previous position that was previously known as kind of tail. So we're going to assert that snake should we call it length? Well, we know the length because it's 1. We just created the snake. So snake get length is 2. And we should also assert that there is an element of the snake's kind of body placed in the previous position. So technically, within the context, we know that the snake can only grow if it collides with food. The food is never placed under the head of the snake, as it were, which can be proved if we use the position that is not the head's body or snake's head. Then any other point is valid, in which case, in order to grow, basically we first need to move, because otherwise we don't have our previous location to grow to, if that makes sense. Snake set direction right, snake move, update, and then we can grow. And then we're going to grow into this point, because our current point is 1, 0. Again, this may, well, arguably this goes against test-driven development because we're combining a few things. However, it does follow the principle of testing it within the context. We know that within the context of the game, the snake can only grow if it moves from starting point to collide with a food object. It can't collide with a food object by just being static, because the food object never spawns under the snake, or at least according to our specification. Let's say we can obtain the body of the snake. So body has item, I think. So we're doing two asserts, which usually goes against some programmers' principles who prefer to have just one assert per the test. Right, so get length is 2, get body has item this, which is our previous location. So we've grown to that location once we moved right. Okay, that sounds reasonable, I think. So we've created method row, we're going to create this method. Now it's an int. Length is just return 0. Do we have one? No, I don't think we should. Just return 0 for now, just to compile the test. Get body, we may need body. Well, we need it to be a list so that we can test if it has an item. Now it needs to be a list of points. I'm not going to create another class saying snake element. I'm going to represent the body of the snake using the point, which is the position of the body element in the game in that particular 2D space. Right, so we can run this now. Length obviously returns 0, we know that. And we need to make it return 2. The obvious implementation here, I think, well, first of all, we need to assign our list. Then, once the snake is created, it has a head, which is the position. So body add position. And length should really be body size, in which case it should now return 1. And finally, we need to implement this method, which is grow. Going to add the previous position. So we need to track our previous position before the move. Let's call it previous. Also, we're growing out of tail, not head. So it's previous tail position, which is at the start is the same as the just position. I'm going to rename position to head, I think. Getter, no. That looks better a little bit. So we've got head, we've got previous tail. And the growth is essentially, well, first of all, we need to remember the previous tail when we move, which is here. Previous tail is body, remove the last element. Actually, now I'm starting to think about the implementation more than about tests, which is not good. Right, so we'll come back to that, because I just had an idea that this should not be a list, it should be a queue, in fact, the queue, because we can add items in front of the queue and remove, do I always remove it from the end of the queue? Anyway, that's implementation detail, and you shouldn't be concerned about that at this stage. So remove the last element, which is body size -1. And that returns the removed element, which was the previous tail. And now we're going to add the new head, because as we remove the last element of the snake and put it in front. That seems like a nice implementation. And the growth is simply add the last element again, previous tail. Let's test that and see if it works. It does work, and we can now proceed. Well, we've done that now, so I'm going to remove that from the list. Snake can die. Okay. Let's do number 6 first, because it sounds like it's easier to implement. Test snake out of bounds. I'm going to create our snake now. Let's put it there. So 24 is going to be the size of our game. And let's see if it's outside. So true. That snake is out of bounds when the game size is 24. That looks about right. Now we're going to implement this size. Oh, it turned false. We know that. And we can now test. We can now implement the actual correct code. It's out of bounds if its head get x is less than 0, or y is less than 0, get x is greater than size, because we can be at the last element, which is if 24, then it should be the 24th element, so it's greater than size. And get y is greater than size. Let's now test this. Yes, it is out of bounds. I suppose you could add a few more certs if you want to really test the code. So it's out of bounds. 25 should set to false. Yes, because if the game size is 25, then we're still within the bounds, and therefore this method returns false. Okay, so out of bounds done. Test snake dies. How do we know if the snake is well, dead? If it is colliding with its body, and how can it collide with the body? It would have to go through almost like all directions, almost. So we start at the center, and that is going to be that. Let's do that. I'm going to actually first need to make it grow, because you can't die if you're just one tile long. create a snake, we'll move it, we'll grow it, we'll make it grow. We'll do that multiple times. I think we need the snake to grow 5 times so it could collide with itself. Let's do 5. We could also do an assertion here and then say whether the length of the snake is 5. Actually, it's 6 because by default, or when it starts, it's 1. Okay, so we made it long enough so that it could collide with itself. What we need to do now is to move the snake up, then left, then down, so that the snake can collide with itself. It's up, then left, then down, and then it should be dead by now. So it is, again, within the context of our game, because in order to test the code properly, you actually need to think in terms of how the code is going to be used. And this also helps with the design of the code, especially for complex systems. And also the code API, or the library API, if you still don't know how you're going to use it, or how your users are going to use the library. In that case, writing the test first allows you to think in a slightly different way about your library. Assert true. Snake is dead. That's pretty much it. We're going to implement this now. Return false, and then run it, get a red bar, and then make it pass. That's the mantra of test-driven development. It's dead. How do we know when it's dead? When it's colliding with the body, or the head is colliding with the body. We know the head position, we know the body, pretty much. So is dead body contains... we can't call contains, because we know it always contains the head. But we do need to know if the body contains the last index of, and conveniently the ID is giving me as the first option for some reason. Last index of head is greater than 0, because the head is going to be the 0th element, and we need to test if the head's index in the body is not 0. Cool. Let's run all of those tests and see if we've done everything. Right, so we've got all the 5 tests running and passing, which is quite important. And, well, we've already done real time because we can update. And that is about it for the snake class. All we need to do is have some sort of wiring class that will bring together the snake and the food object and kind of drive the whole game. Let's call it game. Ideally, you would now write a test for the game as well, but since most of the things have already been implemented, I think you get the idea of test-driven development. So now we're just going to focus on completing the video. Game will take a size because we need to know what the size is. It's going to be final. We'll need to have an update because it's running real time. We won't have render because rendering is going to be done outside. In the update, we're going to update our snake. We're going to then test if snake is colliding with food. If yes, then snake grow and food set position to some new position, which is get random position. If snake is dead or the snake is out of bounds, given the size of the game, then the game is over. What I've done here is kind of like well, it has similar concepts when you write the test, because you're writing against the implementation or against some objects that do not exist yet. So the idea is basically telling me that there isn't a variable called snake. But I've done the logic of it, and now I'm going to add the stuff that needs to be there. Sometimes it works, sometimes it doesn't, and just make sure that you know all the possible implementation techniques that allow you to get to the implementation that you want. That's kind of the takeaway message from this. Food, going to need to create those things now. The snake position should be size over 2, size over 2. So the center of the screen, essentially. The food is some random point, or just... Because if you remember, we assumed that the food cannot be spawned under the head of the snake. So this point can be any point within the game that is not under snake. So by default, I'll just spawn it somewhere else. Let's say 10, 10 will do. Again, assuming that size or 10 is less than size. Actually, we could just call this, I suppose. There we go. All done. It's colliding with food grow, set position. Let's do that. Is over billion, is over false. Let's implement this. Returns point 2D. And it's going to return, well, we'll need a random number generator. This is the seed that I'm going to use. If you're going to test some things beyond this, beyond the scope of this tutorial, so if you're going to write tests for this class, then make sure you use the random seed as in predefined random seed, because you don't want this to be returning random numbers, in which case it makes it slightly more difficult to test that the values return what you need. Okay, random position. Return any point random next int within the bounds of the size. So ideally, here you should also test that random position does not equal to the head position of the snake, because that was our precondition in writing the tests. The tests are only valid if all the preconditions are true. If preconditions are not true, then the tests have undefined behavior. Yeah, that's all right. Okay, so we've done that. I think we've implemented the whole game. The last thing I will do in this video is write the view for the game so that we know it works. Well, we kind of know it works because we've written the test for the model. Just to see it works, we're going to write snake app using the FXGL game framework. Game application. As a side note, if you're going to use FXGL for your games, this is not the standard workflow, because I've written the game first and then written the view for using FXGL. It's fine if you already have the game written in some other framework and then kind of hooking it up with FXGL. But if you're writing the game from scratch, then it'll be a lot easier if you use the FXGL from start. In which case, most of the boilerplate code just goes away. Settings, just going to disable various things that we don't need for this game. Since we didn't actually specify the size in the model, as in the size of each tile, it's interesting that this separation between model and the view allows you to change the view in any way you want. So we can do things like game size, let's say we use 24, I think. Then tile size could be, say, 25. Let's do 30. That means each tile within this game is going to have the size of 30. Set width is tile size multiplied by game size. Same for the height. We'll need our starting point. Then we'll need to create our game, which is going to be the bridge or the actual game model. And then we're going to integrate this game model into the FXGL infrastructure. Game size. On update, we're going to need some sort of throttling, because this on update in FXGL gets called 60 times a second. We don't want our snake game to be updating 60 times a second, that's too fast. So we're going to create that thing, increment it by time per frame. If this is greater than, say, 0.1, then reset the timer and do update the actual model. And let's then, but we're going to render the game 60 frames per second, which is fine. Game update. If game is over, then get display, show message, game up, and exit the game. We don't have access to that yet, so we're going to add access to it. In render, we need graphics context, get game scene, Since there are no node objects, I'm going to use manual rendering using the graphics context. Set fill color blue for the snake. Fill rectangle. Game get snake get body. The body is a collection of points, so for each point we draw a rectangle. Get x multiplied by tile size. B get y multiplied by tile size, and width and height are going to be tile size. So that's snake set fill yellow for the food object. Get food, get position. You could isolate this in a method called draw game object or something, but that is fine for now. Right, let's have accessors. Get for snake, get food as well. And that should do it. Oh right, we need input. We don't have input yet. I'm going to use domain-specific language, which is just easier. On key down, actually. Up, and the code I'm going to call is game set direction up, which means we need to implement this, which we'll call direction, and it is going to call snake set direction. There we go. Go back here. Snake up. I'm going to statically import this. S is down. A is left. And D is right. Okay, let's give this a go. Okay, snake update. Where is it? Head. Oh, we don't have default direction. Let it be right. So by default, it'll just move right. Okay, so I can control the snake now. Let's collide with the wall. Game over. Cool. Let's collide with the food object and why is it over now? Previous tail. Oh, we're adding the head to the end of the list. We should be adding it in the front. Yes, that's fine. This is why I wanted to use the queue. interface, because that'll be easier. Wow, this is hard. So as you can see, we haven't tested it to the full extent, because otherwise all these small things could have been caught during the test. So I should have really tested that when we move, the head is in the front of the body. Actually, let's do that in the retrospect. So I'm going to revert this change to that. And I'm going to make that test fail. Test head is in front or something. So as you can see, we can also, as a side note, that we're repeating the snake code every time. What we could do is have before annotation for some kind of init kind of method, and move this to an instance level variable, in which case we wouldn't need to repeat all of that, in case you're planning to refactor this code further. Right, so we've done that. Snake move update. Let's make it row, because we want to make sure that the head is in the front, and the only way to make sure is if we have length at least 2. Because if you remember, when we started the game, it was fine until I collided with the food object, in which case I extended the length of the snake to 2, and then the game failed. So we first need to grow the snake. So we now have the snake object of length 2. We move it further and test that. Snake get body get 0, which gives the head of the queue or the list is snake get position, because position returns the head. And as you can see, the test fails. So if I'd written the test before running the game, then I would have caught this particular erroneous behavior. And now we're going to fix it by the fix that we already did in the sort of runtime. So this runs now. All the tests now run. So there we go. We can now start the game, and that should be working properly. So in this video, we've looked at how to write a specification from game, and then how to convert that specification into a test suite that we can run to test the model. However, it is important to understand that the tests represent the specification in code. So if the tests do not match the semantics of the specification, then the tests are not correct because they're not testing something that they should be testing. They're testing something that could be slightly different to specifications. In which case, the game will work against your tests, but that doesn't mean that the tests are correct. So there's kind of tiny things that you should be aware of. Right, so we've done the specifications. We then converted the specifications to tests. We then created the code that matches or passes the tests. And finally, we added the graphics so that we can see the game working properly. Right, so this is it for the video, and the code is, as always, on GitHub. And feel free to extend this, especially this class, which is not tested at all. So you will need to create another class called GameTest and do some testing. Things like get random position are of interest, for example. And that is it. Thanks for watching.